doesn't come from an optimal schedule, then that surface can change. And we really don't know if we're making a true comparison between alternative strategic decisions. One way of guaranteeing that we do is to use an exact optimization methodology such as linear and mixed integer programming. So in doing so, the hill of value, and any point along the surface of the hill of value, is going to come from an optimization, a linear program that's being optimized to determine an optimal sequence of mining physicals over the life of that project. The beauty of this is not only do you get an idea of where the ultimate optimal solution is, for instance at the top of the hill, but you also know at the rate of change of the response surface as different strategic decisions are flexed. So each of these combinations is an outcome of a schedule of optimal mining physicals, and by doing so, we know that we're making a consistent comparison, that we're making a comparison of oranges to oranges and apples to apples, not something else. And also by looking at different combinations of hills, by looking at a hill for cutoff versus capacity, and then capacity versus, for instance, mining method, we can get some idea of what the trade-offs are between these different methodologies or these different options. So for those of you who don't follow the area of linear programming, mixed integer programming, what is it? Basically all we're doing with mathematical programming is we're taking a model of the mine plan or some specific area of the mine plan that we have an interest in, and we're reducing it to decision variables and constraints, and then one objective function which represents what we hope to achieve as a corporation, what our overall strategic goal is as a company. That model is in the form of what's referred to as a linear program or a mixed integer program. And the beauty of these types of models is that when they're solved, we know that we can solve them to an exact optimum, or if we can't, we know approximately how close to the absolute optimum we are. So by making comparisons between solutions using this methodology, we know that it is a true comparison, that we are comparing apples to apples, oranges to oranges. By doing so, we can make decisions relating to what the actual recovered reserve should be as opposed to the mining inventory, what cutoffs we should be using, what's the appropriate mine design, and what is the optimal schedule. So by using this exact optimization methodology, not only are we, for instance, maximizing NPV, but we're also maximizing production system capacity by eliminating bottlenecks in the system, and also potentially minimizing per unit cost by, of course, greater efficiency. What needs to also be appreciated is that we reduce project risk. And we do this by having a means of evaluating the sensitivity of that project to changes in potentially important inputs such as the rate of return that's going to be used, the capacities, the costs, and of course, most importantly, usually the exchange rates and the metal prices. Now, this isn't what's classically done in the industry today. And in my experience looking at the applications that are available commercially and what the reactions of the industry have been, I've come up with the following set of responses. First of all, you have to recognize that commercial mine optimization software is based on a very small clientele. There's not a lot of mines out there. They can't sell a lot of licenses. So we have to limit ourselves, or they have to limit themselves to applications of mine optimization that will sell a fairly high volume and a fairly high price. If you want to do anything more than, let's say, pit optimization, pit scheduling, then you have to find somebody that's quite expert at using these packages and that can force the data into the required format to make use of the available commercial solvers. These people, of course, have expertise not only in that software, but also in mine optimization, and they're quite expensive. So what you end up with a product is you end up either with what is essentially a black box, where you put the data in and an answer comes out that exists within a general mine planning package, such as data mine, or you end up using a specialist consultant. The specialist consultant will produce a specialist model for your application, and he'll do it in a scripting language which probably is not very much use to the end user. In other words, you'll get little more than your answer. If you want to have a new answer or reevaluate the problem in the future, you'll have to go back to that specialist consultant once again. In either case, whether you use a black box and force it to give you the answer that you're looking for, or if you use a consultant, you are highly constrained in what sort of applications you can apply optimization to. Also, the applications that you'll find commercially, they are focused on answering very specific problems, such as an activity schedule for resource allocation or a pit optimization. If you want to do anything more, you're talking about projects that will consume a fair amount of time, especially that of very scarce resources, which the most scarce resource in the past has been skilled personnel. And you also require skills, again, consultants. And there's always the risk when using these techniques that a non-expert user will constrain the optimization so tightly that he ensures that he achieves the results that you are already achieving without any improvement in value. Another impression from the industry is that the only applications for these techniques are pit staging and scheduling. And then probably an impression which is quite correct is that in the end, when you're doing optimization, it's based on a model, and hey, all models are wrong. And that's probably true. So you have to have some way of evaluating that. So I want to present a different approach today. And that's based on using math programming. The problem in the past is that, of course, we had mine optimization applications which were very specific and tended to be black boxes. But there's a long history of application of linear mixed integer programming. It's nothing new. It's actually older than I am, which is getting back a ways. But we need to have some way of applying it in a more efficient manner that doesn't require a lot of expertise in the underlying technology, which only requires an expertise in, for instance, the mining industry. So what I'm going to present today is a system that's been designed around applications in mining. It's called the Life of Business Optimization System. It can equally be well applied to a structurally similar technology, structurally similar industry. So I'll let you read that in Spanish if you want, but really all it is it's a mine optimization platform. It's essentially a set of templates that allows you to put together a production scenario associated with a given mining operation, which can include stockpiles, mills, dumps, different concentrators, smelters, refineries, and then wire those together in such a way that you generate behind that a model, a mixed integer linear program, which is then submitted to a commercial solver. We don't develop our own solvers. We think that's probably not an efficient way of using our own resources. But it sends it to a commercial solver, in our case Cplex, to generate a solution and then return the answer in a format that's intelligible, especially such as an Excel dump with a standard schedule of mining physicals that can be then graphed, plotted, and further analyzed. It's not a black box. It's a method of the user being able to generate a mathematical program using his own specifications. And by doing that, we give them the power to have control over the level of detail of the optimization, the time period, the scheduling units that are going to be involved, the financial calculations and the financial model that's going to be used to create a net present value and an objective function, to use alternative objective functions if they want to. This is being ranged to, this product's being applied to a wide range of applications, everything from industrial minerals to surface open pit coal operations, multiple open pit metalliferous, combinations of underground and open pits, and large smelting, concentrating, and refinery complexes. This will be posted on the website for you to download, and just describes the process that's used to get data into the system and then to define the production scenario and produce a solution. Probably a starting point for any modeling process is to define the system, the scope of what is going to be optimized. And this is illustrated for the Prominent Hill case study, which was what was on the title for today's talk. And probably you can't see things quite as clearly as you'd like to, but that system consists of a main pit, a main underground mine, plus actually several satellite mines. And then, of course, dumps for both, a series of stockpiles that are built up and then depleted on an as-needed basis, pre-existing stockpiles for the inventory that was already on the ground at the point where this optimization study was started, and then simply one plant. And the product is a concentrate. We could also have a plant feeding a smelter, for instance, and we could have products being concentrate for export and sale, as well as concentrates going on to produce anode, anode going on to produce cathode, and then final products for sale, including not only the concentrates and the cathode, but also including values coming out of slimes and dross and whatever other product there is that you would care to put into the model. You start simply with loading up data into your mines. You create your mines, and then you create the stockpiles and you create the mills, etc. But you have to wire these somehow together, and that's done by creating links between them, which represents flows of material. Now that material could be ore, it could be waste, it could be concentrate, it could be tailings. You have to decide what it is you're really interested in. But when you're done, internally, this is turned into a network linear program as part of the overall mixed integer program, which is going to be optimized. And that sort of detail of how it's turned into a network linear program is something that you do not need to deal with. You just simply need to wire it up and associate capacities with flows. A series of templates are provided, and these are shown here. So in this application, you can see that the templates include underground mines, open cut mines, haulages, waste dumps, and stockpiles. And these templates have predefined attributes which can be expanded upon that allow you to say, for instance, in the case of the pit, then if we go down through the properties and go to the bin categories for the pit, it's telling us, it's the benches for the pit, I think. It's telling you, for instance, what the required lag interval is between benches when they're being scheduled, what the working space requirements are for the equipment on those benches, and you could also add information such as the mining cost per bench. Likewise, if you're looking at a stockpile, stockpiles obviously have different attributes. And those attributes would, for instance, include what the existing quantities are, what the content of that stockpile is in terms of what the grades are, what material types are in that stockpile, what tonnages are in that stockpile. You can restrict flow into the stockpile in terms of what type of material will go there at what grade. So you can assign different grades to different stockpiles. An example here is shown at Prominent Hill with both the pit and the underground being displayed. So underneath each one of those mining objects there is a mine. So now the question is, from the perspective of the mining engineer, we can run a linear program or a network linear program that says, well, this is what we want to produce from each source.